So, hello everyone. I'm Joanna Wolff, PhD student at Institut de physique et chimie des matériaux de Strasbourg in France. And today I will talk to you about optomechanics of magnetic van der Waals heterostructures. So, van der Waals materials are layered materials where the atoms are bound in plane by covalent bonds and out of plane by van der Waals interactions. These van der Waals interactions being weaker than the in-plane one, it is possible to isolate one or few of these atomic layers in order to obtain a bidimensional materials. The layers from different van der Waals materials can be stacked together, forming van der Waals heterostructure to combine and protect their properties. So the most studied van der Waals materials are graphene, light-emitting transition metal decalcodonide, and also boron nitride. But recently, a new part of this van der Waals study have gained some interest. In 2017, the persistence of a magnetic order in a monolayer of magnetic van der Waals material has been demonstrated, offering the possibility to embed the magnetic degrees of freedom in these van der Waals heterostructures. So since then, a vast catalog of van der Waals magnetic material has been studied, possessing a great diversity of magnetic order. For example, the family of FePS3 and IPS3 are antiferromagnets, whereas the chromium triide are ferromagnets. In this family, you can also find different spin orientation in plane or out of plane one that can be described by theoretical models like Ising, XY, or Heisenberg. Due to the low dimensionality, the physical properties of van der Waals material can be easily tuned by weak perturbation like strain or doping, making it an ideal system to study the magnetism in 2 dimensions. So the research project underlying my PhD is to suspend this van der Waals material over micrometric holes in order to form nanodrums. So we will probe the magnetic phase transition of this suspended material using 2 experimental techniques that I will detail further in this presentation. We will then tune the magnetic order using strain and also see how the light emission of TMDs can be modified by magnetic proximity effect in these van der Waals heterostructures. So first, I will show you the samples we are using for these studies. So here, there is a scheme of a nanodrum. So you can see here the hole etched in a silicon substrate, the suspended heterostructure, and also an electrode that we use to impose a gate voltage between the substrate and the membrane to apply a force by capacitive effects. So here is an optical picture of the sample. You can see here the hole and here the electrode. So how do we make this sample? So in a clean room, we exfoliate the material from interest, and we exfoliate different materials that we can stack together with the pickup technique, and then we transfer this stack over a hole to obtain such a nanodrum. So the first material we choose to study is FePS3, which is an air-stable Ising antiferromagnet, and its phase transition temperature between its paramagnetic and antiferromagnetic phase is about 120 Kelvin. So the material is not alone in this sample. We also have graphene that is used to make the electrical contact with the electrode since it's a metal. And then we also have WS2 and boron nitride, which are here for fabrication process. So now the goal is to probe the magnetic phase transition of FePS3. So for this, the first method we can use is optomechanics. So optomechanics is a field of physics that focuses on the interaction between light and mechanical degrees of freedom. So the mechanical degrees of freedom will be here as a bidirectional mode of the membrane. So the displacement of the membrane can be described as a drive-damped harmonic oscillator. And we will be interested in its linear response in the frequency domain. So the displacement of the membrane will be proportional to the external force with proportionality coefficient chi, the mechanical susceptibility. So if we apply no external force on the membrane, it will still move due to thermal motion. So here we will detect first the Brownian motion of the membrane, which is modelized by the Langevin force. So for this, we use an interferometrical detection. So we focused the laser on the heterostructure. So we focus the laser on the heterostructure. So the light will be reflected not only by the membrane, but also by the substrate, forming a Fabry-Perot cavity. And the length of this cavity will be modified by the motion of the membrane. So the motion of the membrane will be encoded in the reflected light and sent to a photodiode and then to a spectrum analyzer. So the spectrum analyzer will measure the displacement spectral density of noise, which is proportional to the spectral density of the Langevin force. So finally, we obtain such a spectrum, which contains one peak that will correspond to the fundamental mode of vibration of our membrane. So this spectra has been taken at 144 Kelvin, and the signal is quite low and the integration time quite long, since the signal is proportional to the temperature, and we want to reach even a lower temperature to probe the phase transition. So to decrease the measurement time, we'll drive the motion of our membrane. So for this, we apply an external force, and we will apply it, as I said before, using capacitive effects. So we will apply an alternative voltage at around the resonance frequency of the membrane. So we obtain such a spectrum. So we can see here 4 peaks, which will be the 4 first vibrational mode of our membrane. So in the following, I will only focus on the fundamental mode of the membrane. So we will now see how this mode evolves when we vary the temperature. So there is here 3 spectra taken at different temperature, and you can already see that there is a shift in frequency of this mode. So if we plot all the modes together, like seen from above, you have here the temperature and here the frequency. You can see already that there is a different slope between these 2 lines, and it will be the sign of the phase transition. So to see it more clearly, we can fit the data, extracting the resonance frequency and the quality factor, and then plot the resonance frequency against the temperature. So you have here this breaking up slope that we can see. So why it is so? So the derivative of the square of the resonance frequency with respect to the temperature is in fact proportional to the thermal expansion coefficient of a material, which is also proportional to the specific heat of this material. And as we know from statistical physics, the specific heat has a discontinuity at the phase transition. So if you plot the derivative of the resonance frequency squared, you will see a discontinuity at the phase transition, so which is here, and indicates the phase transition at the temperature around 109 Kelvin. So you can also be interested in the quality factor, because the inverse of the quality factor is proportional to the temperature times the specific heat, and you have then an inflection point at the phase transition. So it confirms the result of another team on the same materials. So for us, we have another technique to probe the phase transition, which will be optical spectroscopy. So on the same setup, we can do optical spectroscopy. And here for FEPS3, Raman spectroscopy is the most appropriate tool. So Raman spectroscopy uses inelastically scattered light to probe the crystalline vibrations, so the phonons. And for this, we focus again the light on the heterostructure, and we recover elastically scattered light on the spectrometer using a long-pass filter. So we obtain such a spectrum. So each peak of the spectrum will represent the vibrational mode of the atom in the crystal. So since we have more than one material in the heterostructure, we have peaks originating from FEPS3 that we are of interest, but also on WS2. So we will not care about these peaks, but only on the one of FEPS3. And even then, we have some distinctions. We have these 2 peaks that arise from the vibration of the bipyramid P2S6 for minus, and we have P1 and P2 that arises from vibration involving iron atoms. And since it is the iron atoms that bear the magnetic order in FEPS3, we will look in priority at these peaks. So now, if we add the spectrum below the phase transition temperature, we see that the striking element is that the appearance of P1A that will characterize our phase transition. So if you plot all the spectra around the phase transition temperature, you can see that when the temperature decreases, you will have the appearance here around 110 Kelvin of this peak P1A. So if you plot the height of P1, you have two different behavior. One before the phase transition, where it is almost constant, and after, where it's increased rapidly. So you can determine an approximate phase transition temperature from around 112 Kelvin. So to sum up, we fabricate sophisticated suspended magnetic heterostructure, and we develop two complementary methods to probe the phase transition into the magnets. So for the future, we are also interested in another 2D magnet, which is NiPs3 and has an in-plane magnetic order, but also possesses light emission, so excitant in these materials, as you can see from these first results. And the next project is to tune the magnetic order and also the photoluminescence in these materials with a suspended sample that you can, as you can see, is already vibrating. So to finish, I will thank my team for their support and also the AtC Nano platform that helped us to build this sample. Thank you for your attention.
Thank you, Joanna, for the nice talk. I don't know if there is anyone that can ask a question now. Maybe you can raise your hand or write it in the chat if you are shy. No, there is no question. In this case, I may have one. So you, for your future, you say that you're gonna prove this other magnet. Do you think you can spread your book of different materials? I mean, can this approach be applied to different materials apart from this one you did and this one you're expecting to do?
Yeah, normally from spectroscopy, it depends on the spectrum of the material, but there are oftentimes when there is peak that indicates the phase transition. And from the optomechanics, normally if the specific heat has the discontinuity that is important enough, you can see it with the other material less.
Okay, so there is no limit.
Maybe if the specific heat has a too small discontinuity, it can be harder to see, but it's still possible normally.
Okay, thank you.